About sulfonate esters in the chapter of alcohols, and we left off looking at the mechanism of how the sulfonate esters are going to help us as being a good leading group. Last time we were in a lecture all together, I mentioned that sulfonate esters end up being a better leading group than the halogens, or alkyl halides. And the reason for that is if you look at the sulfonate itself, when you basically attack it. So the sulfonate ester would be here, right? If you attack the carbon that was basically the carbon that was formerly on the alcohol, right? This is that same R group here, and you pop off the sulfonate, then you can draw at least 3 different resonance structures where you're basically sharing that negative charge over 3 atoms. But then I said for a more typical commercially available reagent, the R group for this sulfonate ester is usually an aromatic ring, which means on top of the 3 resonance structures that we can draw here, we can resonate that negative charge into the aromatic ring even further. And so one of the things that we talk about in OChem 1 with regard to SN2 chemistry is that whenever you have a good leaving group, right, it needs to be happy and stable once it's gone. And the reason for that is you want to prevent the reverse nucleophilic attack. Because all these reactions with regards to substitution reactions are in thermodynamic equilibrium. The question is how do you drive the reaction to the right so that you amplify your products and your yield? And so one of the ways we can do that is to use the sulfonate ester, which is an amazing leaving group. Now, how you might see that in practice with regards to an examination, let's say you had the following alcohol, so here we have benzyl alcohol, the abbreviation for the reagent for the tosylate, for the sulfonate ester is known as tosyl chloride. So that's TOSYL chloride. It's usually abbreviated as TSCl. Usually this is going to have some sort of dichloromethane or chloroform or 1,2-dibromoethane, 1,2-dichloroethane, it's an organic solvent. So this is just the organic solvent. We need base to be able to form this reaction to deprotonate the original alcohol. And once you run this reaction using tosyl chloride, this is what you get, right? And so that's the new sulfonate ester. And so in this case, like I mentioned before, this is an extra step in synthesis, just so that the next step, which would be a substitution reaction, can go to a higher yield, right? But this step right here that we've just drawn to produce the sulfonate ester is a high yielding transformation. And tosyl chloride is very, very cheap, right? We typically buy this by the kilo, right? So it's a cheap reagent. We can do this in high yield. Normally what you would see on the examination in peer-reviewed literature and even in the textbook is once you have a tosylate group on there, it's usually abbreviated as OTS, like that. So the examination, I'm not going to draw the actual sulfonate ester with the aromatic ring on it. Like you see here at top, it will almost always be the OTS, all right? Now, the great thing about this tosylate group, and I'll put it over here off to the side, is that it's such a good leaving group that we can use any nucleophile to displace it. And so that is very, very, very powerful chemistry, because in OChem 1, when we get to the discussions about substitution reactions, we talk about all the different nucleophiles that are available, and we talk about how some nucleophiles are stronger than others, right? And a really good example of that would be like water, for example. Water, because it's amphoteric, it can behave as a nucleophile under certain conditions, but it's a rather weak nucleophile. If, for example, you compare it to something like hydroxide anion, or if you compare that to cyanide anion or something like that, all right? But if you have a tosylate group on that, then even weak nucleophiles can trigger the SN2 and displace that sulfonate group, all right? Now, in this example, I'm not showing you a weak nucleophile. I'm actually going to show you what's happened when you hit it with a rather strong nucleophile. So this is an acetylide anion. If you remember that from OChem 1, we talk about how terminal alkynes, that terminal acetyletic hydrogen is acidic, you can pull it off. One of the ways that we can do that, we even talked about it this semester, was if you chuck in potassium or sodium metal, you can pull off that proton to generate the sodium and the potassium acetylide, and that's the acetylide anion, right? So that carbon is a carbanion, it's extremely nucleophilic, it's extremely unstable, it's absolutely reactive, and so what it's going to do is it's going to attack that carbon, right, this carbon here, the benzoylic carbon, and it's going to displace the sulfonate ester bond, and in the process, we trigger the SN2, and we make a brand new carbon-carbon bond, right? And so this is just one example, right? So the idea here is that you can use weak nucleophiles to trigger SN2s, and if we're doing this on an alcohol, this might be something that we resort to if, for example, the typical benzyl bromide or benzyl iodide doesn't really work. Right? So normally we would do an SN2 reaction like we learned in OChem 1 using an alkyl halide, but if the yields of that reaction are not really good, then we would, instead of using the alkyl halide, we would use the alcohol. We'll create the ester here, and then we can displace it with whatever nucleophile we want, and oftentimes that gives us really high yields in that substitution step, right? So that's methodology based, right? So the idea here is you run the exercise, you're not happy with your yields. This is an alternative reaction pathway to trigger SN2 reactions and get the yields that you need or want. Does anybody still need this up? So the other thing we haven't talked about too much is the reduction of alcohols, right? So I mentioned before that when we look at how we produce alcohols, we usually do an oxidation reaction, right? We take a carbon-carbon double bond, we hit it with acid water, that's the acid catalyzed addition of H2O, that's an oxidation step. If you hit it with a hydroboration oxidation, that's an oxidation step. If you hit it with oxymercuration, demercuration, that's an oxidation step. So we're producing alcohols via oxidation reactions, and then we can go backwards using reduction reactions. I showed you that we can go backwards. We looked at a few reductants. Some of those, for example, were like lithium aluminum hydride, sodium borohydride, or we can stop at the aldehyde, or we can stop at the, we can go back to the alcohols from the aldehydes or the ketones. We can go from the alcohol as well, all right? And that's one way that we can do that. So if we're not trying to synthesize alcohols via reducing much more oxidized species, we can continue and reduce the alcohol as well. So this next section will be reduction of alcohols. And typically the situation is that putting hydrogen back in there just gives you the alkane. Now, there may be a variety of ways that you can do that. I'm about to show you two ways that this can be done. So here we have cyclopentanol. One of the ways that we can pull that off is that we can hit that with acid and water. This is the typical conditions for a dehydration reaction. So this is chemistry. Going back to the chapter of alkenes from OChem 1. So we can go from the alcohol to the alkene. And if, for example, you didn't want the double bond, you wanted to go all the way to cyclopentane, then at this point it's just more OChem 1 chemistry, which would be a reduction with either platinum oxide, nickel, or palladium and charcoal is the one that we use quite a lot for my exams. All right? And that removes the unsaturation. Now, one of the things when it starts to start to build all these reactions, this is where I started saying methodology is really important. In the first step of this reaction, there's an issue, and there's issue in the second step of this reaction. The first step is if you're looking at a molecule where you have acid labile groups, then that first step of this synthetic scheme might not be something that you want to do, right? Or if maybe you don't have acid labile groups, but you have other groups that have degrees of unsaturation that would be reduced in this step. So maybe hitting your molecule with a reduction reaction that involves plating and charcoal and hydrogen gas is not something you want to do, because you specifically want that double bond to be reduced, but maybe there's other double bonds you want to live on, right? They're not going to survive this step. So there is another pathway that we can take, and that involves generating the tosylate group, right? So this is the reaction we just went over. And so we make the sulfonate ester in one step. And then if you hit this with the reducing agent, lithium aluminum hydride, it will just cleave that off. And so in this case, we avoid exposing the molecule to acid, we avoid exposing the molecule to a reducing gas and platinum and charcoal platinum oxide, and then we can specifically target the removal of the alcohol group itself without having to potentially do damage in other parts of the compound. Right? Now again, I'm talking about a hypothetical compound that this example doesn't show you, because the idea is that I'm showing you these chemical reactions on small substrates, and these chemical reactions can be done on quite large molecules. So if you just imagine that there's acid labile groups or perhaps double bonds somewhere else, this might not be the pathway, this might be the way to go. Or vice versa, for example. This pathway on the left might not be the way to go. If you have LAH possibly doing a conversion somewhere else that you don't want. So you have to really think about how to design the synthesis once we start having all these chemical reactions under our belt, which, let's face it, all the chemical reactions I've given you, look at everything from OChem 1 to what we're adding to what we've added to now, it's becoming quite substantial, all right? Which is why I always say from OChem 1 that OChem 2 is OChem 1 on steroids. But it also means that, you now have all these recipes, you need to be able to use them wisely. All right, so these next reactions are alcohols to alkyl halides. So we've seen reactions that go from alkyl halides to alcohols. This is obviously going the other way about it. The simple way that doesn't always work, and also, we can be judicial about whether or not we even want to do that, involves reacting the alcohol with the mineral acid pertaining to the halogen that you want to put there. So this would be hydroiodic acid, this would be hydrobromic acid, this would be hydrochloric acid. But at the end of the day, this is kind of a nasty reaction because you have to work with the mineral acid. Hydrochloric acids, it's kind of nasty stuff if you think about it. So is hydrochloric acid, so is hydroiodic acid. You might have acid labile groups in the molecule, which means this chemical reaction might not be a good choice. If you've got other groups, it might cleave under those conditions, right? And some groups that come to mind that we haven't covered yet are, for example, amides and esters will cleave under acidic or basic aqueous conditions. Lo and behold, there are other ways we can do that. So if you take something like that, in the presence of zinc chloride, we can pull off the chlorination of an alcohol, right? And that doesn't involve using a mineral acid. One that I like to run that has served me well over the years is the conversion of 3 molar equivalents of an alcohol using either phosphorus trichloride or phosphorus tribromide, PBr3 or PCl3. Right? So depending on the halogen, you get to choose from either of those, and you generate 3 molar equivalents of either the alkyl chloride or the alkyl bromide. Right? And that reaction usually is very high yielding. The workup is not complicated at all. I would rather go to that before I think about using HBr or HCl. If you want to put iodine on there, you can react 6 molar equivalents of your alcohol with phosphorus and 3 molar equivalents of iodine to produce 6 molar equivalents of an alkyl iodide. this reaction works with primary and secondary alcohols, not tertiary. And then the last one, which works really good for producing alkyl chlorides, but is really sensitive to the techniques and the preparation of the glass, involves using a reagent known as dinochloride. And we've seen dinochloride in other synthesis, and then we're going to see in the chapter of carboxylic acids and carboxylic acid derivatives, because it is the reagent that we use to generate acid chlorides. So dinochloride is really reactive. It needs to be stored in the freezer, parafilmed really well. If not, it starts to decompose and becomes really gross and generates nasty hydrochloric acid gas, SO2 gas. This reaction is really nice because when you use it, it retains stereochemistry. And so what that means is if the alcohol you're working with happens to be a chiral alcohol, right? You have to remember all those things we learned in OChem 1, right? If the mechanism is an SN2 to bring about the alkyl halide from the alcohol, then you have inversion of stereochemistry, right? So if your alcohol is an R stereoenantiomer or an S, R becomes S, S becomes R. If the mechanism happens to be one that's SN1, you know that it's racemization. R becomes RS, and S becomes RS, right? This retains the stereochemistry, and so this kind of chemistry is really good if you're working with chiral substrates or chiral alcohols. And it retains the stereochemical identity of your starting materials. And that can be really useful. Again, especially if you're synthesizing pharmaceuticals or drugs that are going to be biologically active. That discussion that we have on stereochemistry when we do all those hard drugs together should come to mind. The story about thalidomide, for example, the quote-unquote demon babies, stuff like that, is compelling enough for us to be careful about how we synthesize these things, and then make people eat them. That's such a weird way to think about it. So usually I take medicines. I'm kind of eating. Eat medicine, drink medicine. The doctor tells you so. He's not trying to kill you, he's just trying to make money. I'm just kidding. He signs an oath. He could lie though. Anybody studying this up? All right, so if you've looked at the syllabus since the first day of class, or the first week of class, one of the things that's uniquely tied to the chapter of alcohols, aside from diols, is the chapter of ethers and epoxides. And then ethers and epoxides are not separate chapters of each other. The chapter is ether and epoxides. And so I like to tie it into alcohols. I have them clipped together as a single packet because the chemistry is quite, very similar. You use alcohols to synthesize both of these groups. And so I'd like to now kind of shift gears and teach you a little bit about the chemistry of ethers and epoxides. Now, I know you've slept since then, but if you remember, that is the generic formula for an ether. And when it comes to epoxides, for those of you who had me, it's party hat, right? And the epoxide is nothing more than a cyclic ether. The naming of these things is actually really straightforward. All it is you look at what's attached to the oxygen atom on the left-hand side, on the right-hand side, then you say those things in alphabetical order with the word ether at the end. It's really easy. So if you look at something like this is a methyl group on the left, and on the right is an isopropyl group, right? So this would be isopropyl, methyl, ether. Very easy. So then, you might have used or come across DEE, which is short for diisopropyl ether. It's just oxygen with two isopropyl groups. One that we commonly use in my lab is diisopropyl ether. We use isopropyl ethyl ether, we use dimethyl ether, right? So the names are not mysterious at all. They pretty much tell you what the structure is right off the bat, right? So something like this, if you remember the aromatic ring as a functional group is now benzene, it's phenyl. On the right-hand side of this molecule, we have ethyl, alphabetical order, ethyl phenyl ether. So if the ether is the functional group that takes the base name, then the nomenclature should be no problem. Which probably means that on the examination, I might give you one or two problems like that because it's a little too easy. But that also begs the question, right? Like, well, what if it doesn't take the base name? What if there's another functional group that takes the base name? And then, of course, you'd have to go back to that page in the discussion of alcohols that I told you was the one time I'm going to give you the hierarchy of the different groups. And so if you dog-eared that or have a tab on it or whatever it is you did to keep that page, readily accessible, then you'll find that in this molecule where we have an alkene and an ether, the alkene takes priority. So the alkene's going to get the base name here. And so the ether as a functional group is called some sort of oxy, all right? And so if we look at this molecule, here we have a cyclohexene. And if you remember in naming these things, if cyclohexene, the alkene is the base name, then we're going to number the longest chain, making sure the numbers go through the double bond, which if we're dealing with something like this, means we start from one of those carbons. So we can either start here and go clockwise or counterclockwise, but part of that rule is you got to go through the double bond itself. So if we decided to start here, we'd have to go down 1, 2, 3, 4, 5, or we can start from the bottom carbon and go 1, 2, 3, 4. That would give this functional group the lowest number possible. The alkene is already going to be carbons 1 and 2 no matter what. So the correct way to number this would only be like this. And so then this group right here is what we're going to have to put first. And what that is it's tert butoxy, right? So it's the ether functional group, or the ether as a functional group. It's determined by what's attached to it. In this case, this is a tert butyl group, so this is 4 tert butoxy. And then the double bond starts at carbon 1 cyclohexene. This other aromatic group is difunctionalized upstairs and downstairs. For this one, you can number this either a 1,4, or you can use what we learned was the formalism for something that's 1,4 would be para. So there's two ways that we can name this, both would be correct. And then what we're looking at is, well, what kind of groups are these? Well, that's a methyl group attached to that ether bond. The base name for this is going to be some sort of benzene. So that's going to be methoxy. So this can either be 1,4-dimethoxybenzene, or it could be para, so we can just put p-dimethoxybenzene. And that conveys the same information. And then, of course, if they were at the 1,2 position, that would be ortho-dimethoxybenzene. If they're at the 1,3 position, that would be meta-dimethoxybenzene, right? So both of those work just fine. When it comes to the synthesis of ethers, they're made pretty easily, actually. And I think this semester you were supposed to do the Williamson ether synthesis. Did you guys do that reaction? So I remember there was an issue that we were kind of short on alcohol in that reaction. So I think some of you might have done it. Some of you, if you were in the two lab sections that, I sort of had my group take over, we did different chemistry that wasn't Williamson ether synthesis. You guys weren't missing anything. It's pretty straightforward chemistry. And it works pretty well. But this is a named reaction, which means you can probably bank that Dr. Wilson's going to put it on the exam. And I don't usually refer to myself in the third person, but that's me pretending to be you, pretending to ask me whether or not it's going to be on the exam. So I would argue that it's not really me referring to myself in the third person, it's me pretending to be you, pretending to ask me. Does that make sense? That does make sense, right? I say that only because I know people who refer to themselves in the third person, but that's not what they're trying to do. They're usually just social weirdos. All right, so this reaction is pretty straightforward. It uses a chemistry that I sort of alluded to before, the fact that alcohols are acidic. You can expose an alcohol to elemental sodium, you can expose an alcohol to elemental potassium to generate the alkoxide anion. A reagent that can also do that is not elemental sodium, it's reactive but not as reactive as pure sodium, would be sodium hydride, NaH, all right? And so sodium hydride pretty much is a safer way to deprotonate alcohols, and so what this generates is the sodium salt, all right? And so in this case, we started out with cyclopentanol. So what we end up getting here is the cyclopentoxide, sodium salt. And then this right here, because that's O minus, it becomes a really good nucleophile. So we can do really, really easy SN2 chemistry. And if the substrate for that nucleophilic attack was methyl iodide, right? The electrophilic carbon is the carbon on the methyl losing electron density to the iodine. So there's a nucleophilic attack. Iodine now pops off as iodide. And lo and behold, we get this. So you have cyclopentane on one end and methyl on the other. So this would be cyclopentyl methyl ether. And because it's been a while since we drew something in the chair conformation, I thought we practiced some chair conformation today. I'm always out of practice. Hey, that doesn't look half bad.
Hi, are you Jasmine? Oh, I didn't go to class that day. Yeah, I texted you on Google Meet. Sorry, I don't know.
So I don't keep track of who's taken this class before. If you've taken this class before, I don't want to hear your mouth when I ask this question, because then you're going to spoil the fun. What compound is that? Every time I ask this question, I'm shocked. How are you supposed to know what compound that is? Did somebody ask that in another class? What's your major? Bio major? Advanced major? Prove it to me. What's that? Yeah, that's sugar. That's sugar, folks. C6H12O6. You've been writing it since probably middle school, maybe high school. And you've been writing it forever, and you've never once seen the structure, so that when Dr. Olson shows it to you as you're now a rising sophomore, going to the junior, of all the classes you've taken, right? So first year you take Bio 1, Bio 2. What do you take along with OChem 2? Is there any bio classes you take along with this? It's micro? What's that? Genetics? There's a lot of sugars in genetics, right? Yeah. And that's why when I showed you that The dehydrogenase pathway, that's the cartoons. They always show a little oval, and then they write sugar in it. They never show you what that oval is. It's usually that, or something like that. That's sugar, people. Now you know what it looks like. I have a shirt that I haven't worn that a student a year ago made for me, and sometimes I'll wear it. Maybe I'll wear it. I gotta find it. It's in my closet somewhere. And on the front, it has the structure of that sugar. And on the back, it says just sugar. And the student made it because of the answers that her class did not give me when I asked the exact same question. Anyway, think about that. Anyway, if you look at sugar, and if you look at, any of the sugar derivatives, a lot of them are linked via ether bonds. If you look at polysaccharides, for example, which are polymers of sugar, things like this, a lot of those have free alcohols, and you can do chemistry on those alcohols. Some chemical reactions, which are beyond the scope of this lecture, can specifically target some of those alcohols that are secondary alcohols. Some of them can specifically target the alcohols, primary alcohols. So if you look at the structure of sugar, you can see, for example, these right here are 4 secondary alcohols. This makes a primary alcohol. But when it comes to, for example, putting methoxy groups in their place, the Williamson ether synthesis is a really good example of that you can do that. So methyl iodide in the presence of silver oxide can basically methylate all the alcohols on the different types of sugars, whether you're looking at glucose, fructose, or sucrose, it'll do that transformation. All right. Is anybody still with that? All right. That question specifically for the pharmacists and would-be doctors in this group. All right, alkoxymercuration of alkenes. Now, this reaction should remind you of OChem-1, one of the 3 chemical reactions that we learned in OChem-1 to generate alcohols from alkenes was oxymercuration demercuration. All right, that was the addition of hydroxyl groups across a carbon double bond in a 2-step process in Markovnikov fashion. And the reagents are basically the same. This one's going to be a little bit different, but the reagents from OChem-1 can still do the same thing. Now, if you remember, it's a 2-step process. I'm going to show you right here step 1. Now, where it's going to differ from what we look at in OChem-1 to generate the alcohol is that it's an organic mercury reagent, but that reaction is run in water. Okay? If you run that reaction in water, and then in the second step you reduce it with sodium borohydride, you get the alcohol. Now, if you make the subtle change of not running this reaction in water, but running it in methanol, all right, and then you hit that in the second step with sodium borohydride. So all we're changing is the solvent. Then rather than getting the alcohol in Markovnikov fashion as we learned in OChem-1, you can get the methyl ether, which means that if you run this reaction in ethanol, you can get the ethyl ether, terbutanol, the terbutyl ether, all right? And this was one of the 2 of the alcohol reactions that follows Markovnikov. If you remember, the one that doesn't follow Markovnikov is the hydroboration oxidation. That was the one reaction that I said in OChem-1 that was the only one I'm going to expect you to learn was anti-Markovnikov. If you look at the textbook, there's reagents that you can spike these reactions with that will generate anti-Markovnikov products, but I don't teach that. It's in the book if you want to learn it. That's OChem-1 stuff. But this is the difference, right? All we've done is change that from water 2.5%. The review for exam 3 is up, right? You guys looked at it? Is there a web of doom on the back of that one? Yeah? All right, cool. For those of you who've never taken me before, take a look at that review. Take a look at the web of doom. I never called it the web of doom. Students called it the web of doom. I'm just telling you what other people called it. It's not impossible, but if you wait to the last minute, it's like being broadside by the web of doom. If you wanted to hydrolyze the ether bond, the ether bonds are surprisingly stable to acid aqueous solutions. If you use hydrochloric acid, for example. If you use hydrobromic or hydroiodic acid, those acids are strong enough to cleave the ether bond. So HBr in water at reflux, right? So this is where you have a condenser, you're boiling the solution, and it's condensing and dripping down. You can cleave the ether bond. All right. And this reaction, just to annotate your notes, HBr and hydroiodic acid work well. HCl does not. And that's a good thing because it is not uncommon for you to have an ether functional group somewhere in a molecule, and then you need to run a reaction that involves the use of low pH. And so HCl would be the acid to go to if you want to maintain that ether bond. Now, I know you slept again since OChem 1 in the discussion that we had of acids and bases. We were looking at the effect of electronegative atoms on decreasing, or I should say increasing the acidity of an acid. And, one of the weak acids that we looked at was acetic acid. But then there was one example that I give in OChem 1 that says, hey, if you put 3 halogens attached to the carbon of the carboxylic acid, the pKa of that just drops substantially. And suddenly you have a carboxylic acid that is a pretty strong acid rather than being a weak acid. And that one was TFA. And the molecular formula for TFA is this, and it is trifluoroacetic acid. And it's going to be abbreviated when you see it on the exam, and usually most places is TFA. Right? And that stuff is fairly nasty. This stuff, you gotta be really careful with it. If you put it into a glass, it will etch the glass in no time. And it's also strong enough to break ether bonds. And so, this stuff, you'll have to put it in an ice bath with a little bit of water, and you can cleave ether bonds with it without having to use a reflux mixture of HBr or hydroiodic acid. All right, so that's all I've got to say about linearized ether bonds. All right, so what we're going to do now is look at cyclic ethers, which are known as epoxides. And I'm going to show you that outside of ethylene oxide, which you've seen as party hat for those of you who haven't heard one. There are many more cyclic ethers. You can have multiple oxygen-containing cyclic ethers. One of them is a very well-known organic solvent. Two of them actually. One of them being better than the other. I'll show you in just a minute. Does anybody still need the sun? All right. So cyclic ethers. Also known as epoxides. The one that we are familiar with is the ethylene oxide, which is just that. But a real common organic solvent is one that looks like this. It's typically called dioxane. 1,4-dioxane is a really nice organic solvent. It falls in this category of being a polar aprotic solvent. Now, one that is very common is this one. This is tetrahydrofuran. Now, in OChem 1, I introduced this molecule just because one of the first reactions that we learned in OChem 1 involves using THF as an organic solvent. So to keep you guys from freaking out, is that a reagent? No, it's an organic solvent. I tell you that it's an organic solvent, it's boiling point somewhere around 60 degrees Celsius. I show you the structure, but beyond that, we don't really talk about it very much. But yeah, tetrahydrofuran is an epoxide. It's a really, really common cyclic ether. So, if you're working in a research lab of some sort, you won't be surprised if you see 4-liter bottles of this stuff laying around. Now, the one thing about ethers, cyclic ethers, that are near and dear to my heart, because I am technically a supermolecular chemist by training, and we can define supermolecular chemistry as chemistry beyond the molecule, meaning that we're not interested in the behavior of individual molecules, but we're interested in the behavior of molecules as an ensemble. How do they behave together? Do they undergo self-assembly? Do they exhibit emergent behavior when they start to act as an ensemble that you cannot predict from looking at the individual molecule? That's supermolecular chemistry. And that's a really huge umbrella term, because supermolecular chemistry owes its origins to biological chemistry with regards to enzyme-substrate interactions. The idea that if you have the tertiary or quaternary structure of a protein that somehow makes a binding pocket for a molecule to bind, or perhaps even a binding pocket for a chemical reaction to take place. So we're talking about enzyme catalysis now, right? All that is supermolecular chemistry, because those are multiple molecules coming together to do one thing. Another example of a supermolecular complex would be when you have complementary strands of RNA. If you throw complementary strands of RNA in solution, they undergo self-assembly. They will meet each other and organize precisely because the base pairs would have been met up, and they would form, the DNA helix. Those are all examples of self-assembly. Those are all examples of what I would argue is supermolecular chemistry, chemistry beyond the molecule. All right. Now, because I dabble in that chemistry of my own, the origins of trying to develop synthetic systems that can do these kinds of things, and what I mean by those kinds of things is molecules that can behave as hosts to binding other chemical species, is crown ethers, right? And so if we look at what a crown ether is, it is a ginormous cyclic ether. This particular one here has 4 oxygen atoms in it. And naming these things is actually really easy. The way to name it is you simply count how many atoms are in the ring total, right? So for example, it's carbon, 1, 2, we count the oxygens as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 atoms in the ring. We're not counting hydrogens, all right? So we'll come back and say, all right, that's 12. You write the word crown and then you put the number of oxygens in the ring, for which is 4. So the name of this macrocycle is 12 crown 4. And the advent of supermolecular chemistry really came from the Nobel Prize winning work of two faculty, one was in industry. One was named Jean-Marie Lane, who was over in France. The other one was Pedersen, who worked for a chemical company in the United States. And the third one, so it was Pedersen, Jean-Marie Lane, the other guy was at UCLA, Donald Cram, that's what it was, Donald Cram. And what they noticed was that if you have something like 12 crown 4, which they synthesized, they made the note that these are electronegative atoms. So at these points here, you have negative charge, and they figured out that ions would bind very, very strongly to the inside of these macrocycles. And in particular, for this 12 crown 4, lithium cation binds to it very well. It is a perfect fit for the inside of that ring. And this was the advent of host-guest chemistry, where the macrocycle plays the role of the host, the cation is the role of the guest, and they're designed to fit like a hand in a glove, and when you mix them, that complex will then form. And then they go on to show, well, let's just go for something bigger. And they made and showed that you can synthesize much bigger crown ethers. So we say it's 1, 2, 3, 4, 5. Something like that. What would the name of this one be? Take a shot at it. 15 crown 5, yeah. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 5 oxygens, 15 crown 5. 15 crown 5 binds sodium. Very nicely. Let me show you one more. There's a lot more. I'm not going to give you every single one that was made because that would be ridiculous. You don't want a Nobel Prize for synthesizing 3 crown ethers. The body of work is very, very extensive. But this laid the foundation for what we call supermolecular chemistry. And the idea was that you can now begin to design organic molecules so that they can undergo self-assembly with other molecular species to form complexes. These complexes can range from very, very weak binding to very, very strong binding. This one here is 18 crown 6. This one is large enough to bind very tightly the potassium cation. And then, Donald Cram and Jean-Marie Lane go on to change these structures quite elegantly. They generate molecules known as carcerans and hemicarcerans by putting an additional ring so that you have sort of a macrocycle and you have another macrocycle. That was called the hemicarceran. Carceran coming from the root word that, incarceration comes from. The idea is that it would play a host and it would incarcerate whatever it binds. And then the carceran had 4 different, so it was like 2 macrocycles fused together. So you had 2 rings like that, then a ring popping out of the plane of the screen, a ring popping beyond the plane of the screen, and that one, when it bound the cation, would bind very, very strongly, right? But then the field of supermolecular chemistry has moved on from there, because now you can design organic molecules that can bind other organic molecules. In this case, they're just binding ions. And so now you can begin to develop polymers that can sequester pollutants from the water. You can develop polymers that can specifically sequester pharmaceutical drugs or biological agents, things like that. And that's what we call supermolecular chemistry, and that's just a piece of it, right? In our discussions in OChem 1 about the self-assembly of amphiphils into micelles, which are the surface active species for detergents, soaps, and shampoos, that is also supermolecular chemistry. Those things self-assembling into solution so that the ensemble has a different behavior and of course changes the physical properties of the solution they find themselves in. Right. But it started out with Cram ethers. All right, so that Nobel Prize was shared between Donald Cram, John Ray Lamb, and Pedersen. And yeah, the rest is, as they say, is history. So in OChem 1, we learned that you can use a peroxy acid, the commercially available one that I typically put in the exams, is MCPDA. This is how ethylene oxide is usually produced in the industrial scale. It involves the use of oxygen, silver oxide, heating this up to 300 degrees Celsius, and you can generate ethylene oxide. Right? Now, the chemistry I'm showing you here is just kind of a throwback to OChem 1. So this was the reagent MCPDA. And if you remember, the functional group of MCPDA is that it's a peroxy acid. And a peroxy acid is fundamentally different than a carboxylic acid, although it can be quite confusing if you've never seen one before. But unlike a carboxylic acid, it has an additional oxygen alpha to the carbonyl. And the oxygen-oxygen bond, whenever you see that in an organic molecule, that is a peroxide group. So whenever you look at hydrogen peroxide, it's hydrogen, oxygen, oxygen, hydrogen. So that oxygen-oxygen bond is the active species. It's the active species of this peroxy acid. We have the peroxide bond right there. So one of those oxygens gets delivered across the carbons of the double bond to give us our party hat, our cyclic ether, cyclic epoxide, whatever you want to call it. All right. This goes on to become a carboxylic acid as a side product. All right, and so this is chemistry that you've seen already. And so chemistry that's fair game, this is even true for OChem 1. If you remember this, if water wasn't present, this would be 1,2-dichlorination going through a chlorinium ion that then gets attacked by chloride to open it up. But if you do this in the presence of water, this is halohydrin formation, which means the bond breaks, you get a chlorine and an alcohol group attached. And what I want to remind you is that these chemical reactions that involve the three-membered intermediates, of ammonium ions, of chloronium ions, the mercurinium ions in the case of oxymercuration, demercuration, usually results in products that are stereochemically selected. This one gives us exclusively the trans product. And then if you look at what's happened here, you actually have the stage now set for an intramolecular cyclization, right? If we were to hit this molecule with a base, right, in this case, sodium hydroxide and water, right, what you can imagine is there's only one group on here that is acid-base reactive, and it's the alcohol group. And when you hit an alcohol with a base, you take the proton from it. And so you generate this alkoxide anion. And now the reason it's an intramolecular ring closing reaction is because in the structure you have the nucleophile and you have the electrophile right next door. So you don't have to do two reagents to do an SN2. This will do its own SN2, right? This will then attack the electrophilic carbon that will displace chlorine as chloride, and then you have a ring closing reaction, which gives you the cyclic ether. so these intramolecular ring closing reactions, they're usually pretty elegant, and you can use them to make 3-membered rings, 4-membered rings, 5-membered rings, 6-membered rings, and it works quite well. So what I've shown you upstairs, if we ignore the industrial synthesis using oxygen and silver oxide, is that you can use a peroxy acid such as MCPBA, or you can generate the halohydrin followed by sodium hydroxide. Both of those will give you the party hat or the cyclic ether. Right? So I'm showing these two reactions down here to basically say they're going to do the same thing. Right? But there's a problem that ends up manifesting with the particular substrate that I've drawn here. So we look at that alkene, that is a tetrasubstituted alkene. And whenever you start to make these cyclic epoxides on tetrasubstituted alkenes, 2 of the groups attached to both of those carbons are going to end up popping towards you outside the plane of the screen, and 2 of the groups are going to be pointed backwards. And the problem with that is, well, which one is it going to be? Is it going to be this group and the methyl pointing forward? Or is it going to be the ethyl and the methyl? I mean, there's an issue. And so the problem with this kind of chemistry on tetrasubstituted alkenes is it ends up generating a racemic mixture of isomers from this chemical reaction because there's no selectivity in it whatsoever. So one of those products might look like this, where it is the terbutyl group and the methyl pointing forward, which means over here would be the ethyl and the methyl group pointing backwards. And then you might get that one. And so, early on when we started to look at epoxides, when I say we, I mean the collective we as chemistry and the chemists all over the world back when these chemical reactions were being developed. The fact that you ended up getting these in a racemic mixture, right, which means 50-50 of each, was a huge problem. It's a really, really big problem because you've got 2 chiral centers here, and now you've got 4 chiral centers on 2 different products that you have to contend with. That becomes an issue. And it also becomes the subject of a man's work who's won the Nobel Prize in chemistry, I think 3 times now. And his name is Barry Sharpless, and he's a professor of chemistry at the California Institute of Technology. And I've had the unpleasant experience of meeting him because he's kind of an old man now and he's really grumpy. And I invited him to a conference along with 7 other Nobel laureates, and I can say of all the ones I've met, he was the grumpiest, and I'm being polite. He also has a glass eye that rumor has it had to do with an explosion in the laboratory. I don't know if that's true. More reason for you to wear goggles when you hear about this guy. And so his chemistry that won him one of his Nobel Prize is known as the Sharpless catalyst. And the Sharpless catalyst, or the chemistry I'm about to show you, is pretty complicated, so I'm not going to go over the mechanism. But it solves the problem that I just laid out with this racemic mixture. And so this catalyst is a mixture of a few different molecules. This is one of them. And so here you have titanium with these isopropoxy groups coordinated to it. This is usually written as the following. So obviously I can't be drawing this or have you see this on the exam. So usually you're going to see it as something like that. That's the same structure. This is titanium, tetraisopropoxide. And so, in OChem 1, I sort of allude to the fact that in the chapter of stereochemistry, that you don't get enantiomeric excess out of anything, right? So I mentioned that the hallmark of all biological systems is enantiomeric excess, not only in the amino acids that build up the proteins, but enantiomeric excess in the sugars that we have in our physiological systems. But then when we start to learn about the chemistry that makes chiral centers, we realize that that's not that simple. You usually generate a racemic mixture during a chemical reaction, or you have a version of stereochemistry. So it's extremely difficult to imagine what primordial chemistry might have been going on to lead to the physiological systems and the enantiomeric excess that's their hallmark today. And the reason for that is because some of the chemical reactions, the one that we just went over here, the reason we get a racemic mixture in this reaction rather than one enantiomer over the other is because we haven't put in any stereochemical information to guide it, right? And so what he's done is he's developed a series of two different compounds that provide that stereochemical information that can help guide the stereochemical outcome of the products. All right, so here's one of them. All right, so you'll note that you've got the two chiral centers for the alcohols popping towards us. All right, this will have the positive sign DET. If you remember from our discussions of stereochemistry, that positive symbol tells us that this enantiomer rotates plane polarized light to the right in a positive fashion. The other possibility was to use the other enantiomer. Something like that. So the Sharpless catalyst is actually the combination of a peroxy acid, titanium tetraisopropoxide, and one of these two chiral catalysts. And these chiral catalysts are going to provide the stereochemical information in the chemical reaction. And I guess, when they designed this reaction, the hope was that rather than getting a racemic mixture, you might be able to amplify the stereochemical outcome of one of those products. And so rather than MCPBA, this is the peroxide that they used. All right, so here we have the peroxide bond, dead center. We have the titanium catalyst present in the reaction mixture. And if you ran this reaction in the presence of positive DET, then what he showed was that you can amplify the yield of what is effectively the SS enantiomer with 98% enantiomeric excess. That means only 2% of the product that gets generated in this reaction is the other stereo configuration. So, even then, with this amazing work, we're still not, close to 100%. And when I say by close, that extra 2% is really, really hard to get. But biology has figured out how to do that. And it does it really, really, really well. But this is about as close as we can get. And so then, of course, I think at this stage it's academic. That if the gentleman won the Nobel Prize for this work, he must have shown that by changing the chiral auxiliary to negative DET, that you get the opposite configuration amplified. And he did indeed show that. You can get the RR enantiomer in 98% enantiomeric excess. Now, I don't want you to think that this is, something to sort of yawn at. The body of work that this gentleman did showing his different types of catalysts and oxidants and chiral auxiliaries, he shows it for a lot of different substrates. And he won the Nobel Prize for that because he effectively solved that problem. Let me go ahead and leave this up here for you guys to unpleasant to talk to, it was like, I never knew my grandparents, but I've seen movies where there's grumpy grandparents, it's kind of like that. It's really strange. It's like, dude, I'm the reason we didn't pay like $15,000 to fly to China to get this talk. Like, I'm the guy. No, he doesn't care. 2 Nobel Prizes in at the time. Anybody still need this up? All right, so let me show you what we can do to these party hats once we have them. One of the reactions that I showed you in OChem 1 was that you can actually open them up. And you can open them up with acids and you can open them up with bases. But the base is the one that I want to show you right now, because if you think about what this group is, right? This is definitely a polar covalent bond, right? Which means the 2 carbons involved in the cyclic epoxide are basically electrophilic. So if you were to expose them with, a good nucleophile, for example, hydroxide anion coming from none other than sodium hydroxide, then hydroxide would hit one of those carbons and you trigger a ring opening reaction. And then if you did an acid aqueous workup on it, you could generate the 1,2 diol. And this is a reaction that you learn in OChem 1. What we don't talk about in OChem 1 is that all we have to do now that we see what happens with this is change the nucleophile, and then we can open up that cyclic epoxide ring with a bunch of different things attached to it, right? Because the nucleophile can be a cyano group, it can be a deprotonated sulfur, it could be Grignard's reagent, for example, or an organolithium, or lithium aluminum hydride. all these reagents are now fair game for attacking either one of these carbons of the cyclic epoxide. So the one that I want to show you that is pretty powerful, and then I'll show you all the others. I'm just going to cascade them down the page. Some of them might have to wait until next week. But this is the reaction. You have to hit it up with acid to protonate the alkoxide anion that forms. But this would be a sodium alkoxide, right? So if you take an alcohol and you hit it with sodium hydride or potassium, sodium elemental metal, remember you deprotonate the alcohol, you generate OR minus. OR minus is the nucleophile in this reaction, and it will open up and you can generate your ether bond just like that. All right, so that's one thing that works really well. As I alluded to earlier, a cyano group would work. This is not chemistry I would wish upon anybody to actually do, because sodium cyanide is pretty nasty stuff, but it's a good source of the cyanide anion. Cyanide will behave as the nucleophile and do the attack, and you can open up that ring to generate an alcohol group and a cyano group. In the discussions about how to synthesize thiols, sodium SH, this would be sulfur with an alkyl group attached, same situation, working it up with acid and water. You can generate the carbon-sulfur-carbon bond. So basically a thiol ether. And then I told you this guy's work was super pervasive. Victor Grignard. So even Grignard's reagent, whatever the R group is, that R group is basically behaving as a carb anion. It's a really powerful way to open up that ring, and you get that R group, whatever it was, right there. Or maybe you want to open up the ring, and instead of putting two things across that carbon, you just want a single alcohol group. There's chemistry for that too. And in case you haven't noticed, after I show you this with lithium aluminum hydride and hydronium, which opens up to give us a single alcohol, that is 6 different reactions that you've probably never seen before in like the last 4 minutes of class. So I'm only bringing that to your attention so that it doesn't escape you that you should start studying for exam 3 as soon as you can. Because this chapter is almost done. It's almost done. So we're getting there. All right.